now we can state the theorem. So, what let let f be a function from 0 1 to the power n to 0 1, okay, and let y1 up to yk be disjoint subsets of the domain X x1 up to xn, okay. Then L over B2 of f is greater than or equal to 1 plus 1/4 sigma log of Si, I going from 1 to k, where Si is the number of distinct subfunctions of f on yi. Okay. So, let us try to understand what is going on. So, we take a function f and we look at its domain and we just consider subsets of the domain that are disjoint, okay, some y1 to yk. Okay. So, basically this is basically just collection of the variables x1 up to xn such that no two subsets have a variable in common, but it need not be a partition in the sense that it need not contain all the variables. I am not saying it is a partition, just these are subsets. Now, what we are saying is that if over all these domains, okay, so let Si be the number of distinct subfunctions. Okay. So, here what I define what a subfunction is. So, on a subset y, okay, a subfunction is basically any restriction. Now, I can have many types of restrictions on the same subset, okay, depending on how I fix sigma. So, for various different sigmas, I will have various different subfunctions, and Si is the total number of distinct subfunctions of f on yi. Then what we are saying is that the lower bound of f over the basis B2 is 1 plus 1/4 of log of Si. Okay. So, as the number of subfunctions keep growing, the lower bound will increase. Okay. So, again this is kind of intuitive, because what it says is that, well, if we have a function such that for any restriction it has many different subfunctions, then the function should be complex, okay, which means that it should have a higher formula size, and that is what it kind of means. Okay. So, any questions? Any questions about what we mean by a restriction or what this theorem states? That is the definition. So, sigma, the domain of sigma is z. Okay, z is defined to be x minus y. So, what we are saying is that a subfunction on y. So, if I fix y, now a subfunction on y is basically any function whose domain is z. That is what we are saying. Okay. So, if I fix sigma to be some z, okay, which is sending some elements to 0, some element to 1, then my subfunction is fixed, but depending on what sigma is, I can have many different subfunctions. Which definition are you talking about? Yes. Given sigma, yes, a restriction, this is, so basically here I am defining a restriction. So, a restriction is a function sigma on z. Okay. So, given a function f and a set y, a restriction is function sigma on x minus y, which is sending, yeah, it's a Boolean function on x minus y, which is defined in this manner. Now, how many different restrictions are there? That is basically the number of subfunctions.
What you are referring to as a restriction is that function sigma.
Yes.
Then the number of subfunctions and number of restrictions are different. They are two different versions.
Well, I mean,
So, if a sigma is what you are calling as a restriction,
yes.
the number of restrictions is just the number of functions from that to zero.
Yeah.
But then the subfunctions can, number of subfunctions can be much more.
It can be more, yes. It can be more. Yeah.
Why the number of subfunctions can be the same, right? It can be different. Two different functions are using the same function.
Well, no, it cannot be more, it can be less actually. It can be less because two different subfunctions can be the same over here. Yeah.
Also, in this theorem, disjoint subsets is considered, but not a partition.
No. This is just making the theorem stronger, right? I mean, you can have a partition also, but you need not have a partition.
Let's say it's not disjoint.
No, if it is not disjoint, then the theorem will not work. So, the proof, when we look at the proof, you will see that it crucially relies on the fact that the set of variables are not common. The set of variables of yi's, they are not common.
So, even if this y1 to yk are missing certain elements,
That is okay.
by adding them we can actually strengthen the theorem.
We can, no, we are weakening the theorem, right? Because partition is a more stronger, so this is basic.
That's okay, fine. But if we add the remaining elements as another y k
Yeah.
plus 1, the lower bound will go up.
It, no, the lower bound will stay the same.
But there will be another SI term in the summation.
Yeah, okay, so you are saying that you add one more set which has the remaining element. Yeah, so then, yeah, so then you will have some other SI term. But this is like a more general version, right? So, this will work even when you do not consider all the variables.
Then there will be k plus 1 many sets, and then the theorem statement will have
K plus 1, huh?
So, it's still the.
Yeah. Okay. Okay, so let me talk about the proof. Actually, the proof is not very difficult. So, once this setup is there and once you understand what a function and its subfunction is, the proof is just a couple of observations. So, let Li be the number of occurrences of variables in yi in a formula for phi. Okay. So, consider a formula for phi, any formula, and let number of occurrences of variables. So, now the variables of any formula are always the leaves, right. So, I am only looking at those leaves variables in yi. Okay. I am only looking at those leaves which are the variables from the set yi, okay. And I am going to count this Li. What I will show is that Li is greater than or equal to 1/4 log Si. So, this is what we will show. Now, why is this sufficient? So, basically if I show this for Li, now if I sum all the Li's, that is basically the total number of leaves in the tree. So, that will show that the total number of leaves is greater than the quantity on the right hand side, and the total number of leaves is basically half the size of the entire formula, right, because it is a tree. Therefore, the size of the formula is nothing but the number of leaves. In fact, the number of leaves is one more, that is why we have this 1 over here. So, the number of gates is 1 less than the number of leaves. I am just counting the number of leaves over here. Okay. So, clear so far? Okay. Now, how do we prove this quantity? So, to prove this quantity, let me just kind of give the intuition pictorially. So, consider the formula, the entire formula phi. Okay. So, let us say this is my entire formula phi, and let us say that there are certain inputs which belong to variables in yi. Okay. So, let us say this is some input which is belonging to yi, this is another input belonging to yi, and there are certain inputs which do not belong to yi. Okay. Now, look at all the paths from the leaves which belong to yi up to the root node. Okay. So, suppose this is a path which goes from a leaf to the root node, this is another path which is going to the root node. Here I have maybe some other path. Okay. It is a binary tree. So, okay. And I can also have, let us say, some other node which has a path to a leaf which is not in y, okay, but we will not be considering these things. So, these are nodes that I will not consider, but these are the paths that I will not consider. So, here I am only considering the purple paths. Okay. Now, how many leaves are there? So, the number of leaves is, so the number of leaves is equal to Li, and the number of nodes with 2 inputs will be how many? So, this is, I am only considering the restriction. Okay. So, let me just state this over here. So, consider the restriction of the formula to input gates that belong to yi. Okay. So, I am considering the restriction of this formula to the input gates which belong to yi, and in this formula I am counting how many leaves are there Li, how many nodes are there which have two inputs. So, again it is a sub formula, okay. So, which means that it has a tree structure. So, if I have a tree which has Li leaves, how many nodes are there of degree 2 in degree 2? It is a binary tree. Well, it need not be a binary tree. I mean, I can have a path over here where some of these nodes can have in degree and out degree 1. But if I look at the nodes which have in degree 2, how many nodes will there be? Huh? What? So, again this is, you can go back and look at this. So, this is from the theory of binary trees. The number of nodes of in degree 2 will be Li minus 1. Okay. So, one way to look at it is that if you compress all these paths, okay. So, we have these paths that are present. So, if I compress all these paths and make it into a make it into a binary tree, that is every node has in degree either 0 or 2, then we know that the number of nodes of the number of internal nodes is Li minus 1, 1 less than the number of leaves. But even if I stretch them and make them into paths, it is basically each node has in degree and out degree 1. So, they are kind of cancelling out. So, the number of nodes of with 2 inputs, that is in degree 2, will be equal to exactly Li minus 1. Okay. Now, what we will do is we will consider all these paths. Okay. So, consider all paths from a leaf node. So, let me call this set as x, say xi. So, all these nodes which have or not x is already used, let me use w. So, all these nodes with 2 inputs, let me call them as wi. So, consider all paths from a leaf node to a node in wi or from a node in wi to the next node. Essentially what I am saying is, look at all these paths. Okay. So, here I have a path from a leaf node to a node in wi. So, this is one path. Here I have another path, second. Here I have another path from here to here, third, fourth, fifth, sixth and seventh over here. Okay. So, look at all these paths that are present in this subtree. Okay. How many such paths are there? So, corresponding to each leaf and corresponding to each node in wi, I will have one path, okay, which is basically the path going from that node to the next node above it, correct. So, the total number of such paths is equal to 2 Li minus 1. And what is each path? Okay, so, each path is basically a function on one variable, in the sense that each path takes a value and it is either outputting that same value or it is outputting the negation of that value or it is outputting 1 or it is outputting 0, right, each such path. So, each such path is a function on one variable. There are 4 functions on one variable, 4 such function. So, I can have h of x as being equal to x, I can have h of x as not of x, I can have h of x equal to 0 or h of x equal to 1. So, these are the only 4 possibilities for these functions and for these paths. And now, any sub function, so a sub function is basically just this subtree, any sub function is uniquely determined by these all these paths. So, once I fix all these paths, that uniquely determines a function. So, therefore, each sub function is determined by these paths. Therefore, the number of sub functions is at most 4 to the power 2 Li minus 1. So, which is equal to 2 to the power 4 Li. I mean, I can just leave out this one, which implies that if I take log on both sides, I get that Li is greater than or equal to so 4 Li is greater than or equal to log Si. So, Li is greater than or equal to 1/4 log Si. Okay. So, that completes the proof.
Any choice of values along the path will not give us a function. Right? Some of them may be nonsense.
Some of them may be nonsense, yeah. So, that is why I have it is an upper bound on this. Yeah. Okay, so, I will stop here. So, we will come back to this. So, again next class we will come back to this theorem, we will understand this theorem little more in depth, and then what is more important is we will look at applications, how we can apply this theorem to get lower bounds for various functions. Okay, thank you.